I'm here from Eindhoven University. I'm a master's student of the Department of Electrical Engineering, and I will present my master thesis on the prediction of crack growth retardation following from a single overload application using a subspace encoder network. So to start off, we have, of course, the Paris law, which can be used to compute crack growth during fatigue loading. Paris law, it uses the C and M variable, which are found experimentally. Paris law, it does not include crack closure effects, and it doesn't include mean stress effects. And crack closure effects essentially happens that during a part of the loading cycle, part of the crack faces, they come into contact. And because they come into contact, not the entire loading cycle contributes to the actual crack growth. And Newman introduced a way of measuring this crack closure effect with the stress intensity KOP value, and or you can also use the crack opening force. And over here on the figure on the right, you see the crack opening function plotted for different load ratios during constant amplitude loading. And because you have this opening value, the effective part that actually contributes to the crack growth is always smaller. This delta K is always smaller than delta K. And that's shown also the relation between this ratio and the load ratio during constant amplitude loading is shown over here. So in order to explain the effect of a single overload and how the effective driving force changes, we consider this simplified figure of basic overload and followed by constant amplitude loading. So in green is highlighted essentially the effective part of the loading cycle. As we see, it starts out in steady state. And at the moment where the overload is applied, the cycle after, the effective driving force, it increases. And in the subsequent cycles after, this can be thousands of cycles. Here it's just shown a bit more simple. It can be thousands of cycles, the effective driving force is decreased. So if we look at what it does to the crack opening rate, we see that at the moment of the first it's in steady state, then the overload is applied, it increases, and then it decreases. And eventually it can take thousands of cycles, but it will return to steady state. And we can use this effective stress intensity factor range to, in combination with the Paris law to model the crack growth over time. So there are models to predict the crack growth when an overload is applied, like the Willenborg model and the Wheeler model. And these models, they make assumptions that overloads create a plastic zone, and they assume small-scale plasticity, so that the entire material, except for a small point ahead of the crack tip, behaves linear elastic, and it creates only a small plastic zone ahead of the crack tip, which is essentially this plastic zone over here. And these models, they make assumptions about the size of this plastic zone and how it affects the strength of the retardation. So these models are limited in their generalization to more complex loading scenarios. This is mainly due because they rely on these assumptions about the plastic zone, and load history effects are not encoded in delta K. Other models, of course, also exist, like state space models and Pascal models. However, these models are, they also do not always work perfectly for complex loading cases. And Pascal especially is computationally very heavy. So with this research, we aim to learn the crack opening function directly from using a lot of data. And that way, if we have the crack opening function, we can compute the actual driving force behind crack growth. And we believe that this method might be able to generalize to a lot more complex loading cases. So first of all, we want to create a lot of synthetic data for the AI model to train on. And this data will be created with the Patank array-based state space model. Then we use a subnet approach to learn the crack opening function in terms of crack extension after the overload, delta AO. Using the inputs, the effective stress intensity factor range from the previous step and the load ratio. And eventually we want to evaluate the performance of the trained model on different data sets with different load ratios, different overload magnitudes, and different initial crack lengths. And we do this in terms of normalized mean squared error. And yeah, I should highlight that this is a preliminary study where we just aim to check the feasibility of this approach and see what potential challenges of this approach will be. So first of all, the state space model, it's based on the Patank array state space model. All the data that we create with this state space model only is of one material and only a CT specimen. In fact, it should theoretically work for all other specimens because we model the effective driving force of the crack growth. And as long as delta K effective doesn't change, the results also shouldn't change for other specimen. This state space model uses the crack opening force POP and the crack length A as state variables. And it includes crack closure effects, but it does not include delayed retardation effects. So this is an example of just the data sets that we can obtain using this state space model. The orange line shows data set without overload, and the blue line essentially shows the overload we applied that cycle 50,000, and there's no delayed retardation, just crack closure effects. And moving on to the subspace encoder network. This is essentially a combination of multiple neural networks combined together. We have an internal model state. It's computed using a separate neural network F of data. It's highlighted by this. This network, it tries to predict the internal model state using the previous internal model state and the inputs of the model. And as for the output, we have a separate neural network H of data that uses the internal model state and the inputs. And we assume the initial state with a separate neural network C of data, which is essentially, it takes as inputs the past, a set of past inputs and outputs. And you might wonder, why do you use this complex subnet approach and not a simple artificial neural network? Well, this subnet approach has proven to be super efficient, data efficient, and successful in modeling highly nonlinear dynamical systems. And if we assume that an overload creates a nonlinear response in the system, then this subspace encoder network should also be able to learn this nonlinear system. In the loss function, we use batch optimization for the network. The loss function becomes this, where this is pretty normal loss function. However, we use a local standard deviation, which is unique for each data set, because we train on a lot of different data sets, and each data set has its own variance because it depends on the size of the overload magnitude. And if we do not use this local standard deviation, then you see that the model starts predicting better on data sets with higher overloads compared to smaller overloads. So as for the inputs of the model, we use the effective stress intensity factor range from the previous step and the load ratio, plus the load history, which we assume to be known. And the output is the crack opening function. The open loop, we run open loop simulation. This essentially means in control engineering that there is no observer in the system. There's no formal feedback. So we use each prediction of the model during each step. We use this prediction to compute the input of the new step. So this means that once the model makes a small mistake in the prediction of the crack opening function, this error will stay in the system, and this causes an issue which is called error drift. And there are specialized training techniques to remove this error, where we use a decaying function over time, and this is essentially the probability during training that we use the ground truth values, and that we replace these ground truth values with the model's own prediction. So over time, as training progresses, the model will learn how to deal with its own predictions, and at the very end, these red dots, we save different versions of the models, and in the very end, we use all these versions, and we compare on validation data sets which one works the best, and then we select the best version of the model. So in total, the results were obtained on 1,200 data sets, 81% training, testing 17, that's exactly 200 data sets, and validation was 2%. All these data sets are created randomly with a random initial crack length, which is between 20 and 25 millimeters. And we apply a random overload on cycle 150 to 200. And the size of the overload is also random between 5% and the maximum allowed overload, which is defined as essentially the overload at which crack arrest occurs. So moving on to the results. On the right here, we see the score in terms of normalized mean squared error. We want to get a low score, essentially. Low score is good. The darker colors highlight higher data sets that obtained worse performance. We see that most of the data sets are colored yellow or light green. And this box plot shows the distribution, and we obtain a median score of 0.0299 and an average of 0.1085. Here we see also how these, we have here the load ratio for each of the data sets, the overload magnitude, and the initial crack length, and Kmax of each data set. And we see that most of these outliers here, that they all essentially relate back to this point, meaning that most of the outliers were found on data sets that had a low load ratio of 0.2, which I will discuss further in the discussion. So this is, let's move back. If we zoom in a bit on this box plot and we plot the very best performing data set, this is essentially the result. So this is the crack opening function. The orange line is the prediction, and the blue line is the actual true value. We assume this first part, this is constant amplitude loading. This is steady state. We assume this to be known. These black points, they highlight the initialization part, which is needed for the encoder to start making predictions. And then this is exactly when the overload is applied. And we see basically an almost perfect prediction. Then moving on to the median, this was a data set which scored really close to the median, on a load ratio of 0.2 and an overload of 32%. And we still see that, there is some difference here and some difference here, but it's still relatively good prediction of the model. Then this is the upper bound of the box plot, and we see that it predicts quite well. However, at the very end, it doesn't align nicely back to the steady state. And then we also had outliers. This is the very worst performing data set. And we see, very big difference in the predicted values and the ground truth. So I just showed you this data set essentially, but we have a lot more outliers. In total, we had 20 outliers out of the 200 data sets. And the cause of these outliers is when we have a small loading ratio, the effective delta K effective is higher, and this doesn't scale proportional to each other. So most of the data sets have a relatively low delta K. However, only a small part, only the data sets that are really using a small load ratio, only those really see this high delta K effective. And this means that the model simply during training has not seen a lot of enough data sets on this on this high delta K effective. So there's a data imbalance there, which should be fixed to obtain better results and remove some of these outliers. So to conclude, this was a preliminary study, and we think that it's quite a promising approach to model crack growth over to model crack growth. However, we made a lot of simplifications to essentially test the core idea of this approach. We should, future work should focus on improving the realism of the data. Currently, there is no delayed retardation because we created data sets with a simple state space model. And we did not add any noise to the data, which you will typically find in experiments. However, the subnet has proven to be on other applications to be able to really good in dealing with noise. But we should test that, of course. And we should improve the generalization. We should test with different materials, more loading scenarios, and we should change also the specimen geometry. Also, because we use a subnet approach, batch optimization, and scheduled sampling learning, those methods are quite complex, and you end up with around 19 parameters that you need to tune during training. And we should see if we can try some physics-informed modeling to improve the results even further. And to do real experiments, to obtain real experimental data, it takes a lot of time and effort. So we should see how much data do we actually need to get this method to work. Because if you need millions of data sets, it might not be reasonable to obtain this data. Then, I want to thank my supervisors, Davide and Maarten. And we can move on to the questions. Thank you for listening.